These are your microphones. This is yours, Stefan. That one is yours.
No.
Lasă. Da, așa.
Stai să închid.
Ah. Gata. E de la Ștefan.
Bună seara! Vă mulțumesc pentru prezență. Vă mulțumesc pentru prezență. Thank you for being here. And we want to thank the Italian Cultural Institute for helping us bring Piero here at the 13th edition of Bucharest Science Festival. Profesorul Piero Martin este profesor de fizică experimentală la Universitatea din Padova și, cum spuneam mai înainte, a venit la București cu ajutorul Institutului Italian de Cultură, căruia le mulțumim. Profesorul Piero Martin este experimentalist. Alături de el îl avem și pe Ștefan Ataman, un teoretician de această dată. Cei doi cumva reprezintă cele două laturi ale fizicii. Pe de o parte avem teoria care trebuie să fie confirmată de experimente. Avem experimentele care generează niște date, uneori incomprehensibile, și atunci trebuie să vină teoreticienii să încerce să pună ordine în datele obținute de experimentaliști. Este un dute-vino permanent între cele două specialități, între cele două fațete ale fizicii. Dar nu vom discuta despre această bucătărie internă a fizicii, ci vom discuta în această seară mai degrabă despre un principiu mult mai larg, aplicabil, atât în știință cât și în viața de zi cu zi. Este vorba de modul în care tratăm erorile, în modul în care tratăm greșelile. În fizică, în știință, în viața obișnuită, facem cu toții greșeli, facem erori. Lucrurile, de obicei, nu merg niciodată așa cum ne-am dori. Nu se întâmplă niciodată din prima să reușim. Sunt cazuri extreme, dar foarte, foarte rare în care se întâmplă chestia asta. Dar ce facem atunci când ne-am lovit de o astfel de situație? Ascundem sub preș totul? Sau încercăm să analizăm, să vedem ce a mers prost, să vedem ce putem să facem mai bine, să vedem cum putem să mergem mai înainte. Până la urmă, această atitudine este cheia progresului. Și cei doi vor discuta despre cum o astfel de atitudine duce cunoașterea mai departe. Pentru că de foarte multe ori, analiza acestor erori, acestor greșeli, a dus la rezultate cât se poate de surprinzătoare. Și până la urmă, la asta se rezumă știința, la a merge mai departe într-un teritoriu necunoscut. Atunci când mergi să vezi oare ce găsești dincolo de deal, dincolo de tufișul pe care îl vezi la 30 de metri mai departe, nu știi ce te așteaptă în spate. Și tocmai efortul de a descoperi ce se ascunde dincolo de lucrurile evidente din jur duce omenirea mai departe. O las pe Corina Negrea, care este moderatoarea evenimentului, să meargă mai departe. Și vă invit să intrați pe site-ul festivalului pe www.bucharestScienceFestival.ro să vedeți ce alte dezbateri, ce alte evenimente mai avem, pentru că suntem de-abia în a doua zi a festivalului. Festivalul continuă până duminică inclusiv. Vă mulțumesc și Corina, ai microfonul, nu?
Am headset-ul, da. Bună seara și din partea mea. Corina Negra mă numesc eu, sunt realizator de fizicienii, își permit să fie atât de umani încât să și greșească, fără consecințe foarte serioase. O să fie în engleză discuția, sunt convinsă că nu e o problemă, vreau doar să vă spun că vom lua și întrebări, așadar gândiți-vă să puneți întrebări la finalul discuției noastre. Ok, welcome. I'm very happy to be here with you both, and I am thinking, what interesting mixture. So, theoretical physics and experimental physics. You cannot leave one without the other, no, Professor? Can you live without theoreticians?
Oh, no, I don't. I definitely don't think so. I mean, there is this joke about the fact that there is a competition between theoretical physics and experimental physics, but obviously the two go always together.
Ștefan Ataman, can you live without them? Be honest.
Theoretical physics without experiment is basically a limited edition of mathematics. Okay? We need the feedback. Or theology, if you want to, right? There are much more things in mathematics possible, crazy spaces, crazy structures that do not exist in nature. And if I were just to imagine, let mathematicians imagine, they imagine many things. They have too much time on their hand. So we need physics to tune them down to say, okay, this is how reality looks like, now let's continue.
You need experimental physics.
Yeah. You know, theoretical physics without experimental physics is like spaghetti without tomato sauce. So that's
We cannot imagine
Doesn't
spaghetti
taste
without
anything,
tomato
yeah.
sauce. Okay, but how to say, the proof that you need experiment is what? LIGO and gravitational waves. Yes, the theory was there. The experiment was the final answer.
Yeah, I mean, this is an extreme example because it took 100 years, right?
It doesn't matter. It's an example. It's a good one. Okay.
Yeah, I mean, it was the last prediction of Einstein that had to be proven. And it's interesting to say that Einstein thought that this cannot be done. He was convinced this is impossible to be done. And many people were convinced.
That is not possible.
That it's not possible because it's something they measure. I had difficulty with colleagues of mine to explain them that it's not a trick because they said, how can you measure a distance that is 10,000th part of a proton, knowing the uncertainty principle and all the wiggling and temperature and stuff? How can you measure such a small distance? And I tried to explain them that if you do it collectively, they don't measure one proton, they measure the mirror, right? Which is averaged about 10 power 23 or something, right? And so the physics is there and it's clear, but even to physicists it's so confusing.
I will stay here just for a little while, and I would like to ask you, Professor Martin, how did you feel when the experiment proved that there actually are gravitational waves?
Well, I think that on one end, of course, it's something very exciting. On the other end, it's also, a confirmation that, as we were saying, nature talks always, and nature always comes first. And in this case, nature talks through the experiments. The experiments are sort of the language, and the physicists use to understand nature. And so, we can make a lot of theory, we can make a lot of prediction, but at the end we have always to listen to nature. That sometimes takes time, like in this case, or like maybe a shorter time, but with the Higgs boson was the same thing. And for fusion, which is the field that I'm working on, something similar is happening. We do have theory, we do think that this is working, but eventually we need experiment in order to be sure that this is going to happen.
Because you mentioned fusion, so we don't have yet, yes, as a, how to say, as a resource that we can use. We are still building. And I know that I asked you during the interview, but now it's a different moment. So what do you lack? Knowledges, understanding, better theories, or technology, or both?
Well, I think that one thing that we lack as a humankind at the moment is the will to solve this problem. I know that this seems to be a very general answer, but in my opinion, we are still doing too little in order to solve the energy issue. We know that we have an issue. We know that we have to find a way out from the fossil fuel world, but on the other hand, we don't do enough. There was one number that I gave this morning. Also, I was in a school, and one of the students, we were discussing, following one of the questions of the students about that, and I quote one number that is very important. For every euro or dollar or whatever that you spend in weapons, in military things, only 1 cent is spent in research on energy, which includes everything, also fossil fuels. So it's 1 to 100. It's a gigantic proportion, and interesting enough, this might seem, just a complaint of a physicist, of a scientist, but it has a lot of implication, very practical, that people really, and in particular governments, don't consider, because we have seen already with the Ukraine war how much important is energy for peace in the world, and how much energy is strategic. When Russia decided to cut the gas flow to Europe, this was more, to some extent, as dangerous as a real war, because it could have a gigantic impact on the economies. And on the other hand, if you put another exercise that I suggest the student to make, if you take a world map and you map all the wars that happened since the Second World War to now, and you map where the oil or gas reservoir are, the two maps are more or less coinciding. And the reason is that with energy there is a lot of interest, thanks to all what is happening in the Middle East. A lot of that has to do traditionally with the issue of energy. So energy is a strategic asset, but we are not doing enough. And in this respect, I go to your question. This is a starting factor for fusion. Up to now, fusion is complicated. It's a difficult problem, but up to now we have invested really too little in order to tackle this problem.
Invested in what? In theory, in developing?
In human being, I would say, because after all, are the scientists that have to solve this problem. And up to now, we simply had too few people working on the subject. Of course, we still have to solve scientific problem. We have to solve some technological problem. But I'm really very confident that if we are serious enough about the problem, we can drastically accelerate the development.
Stefan, I know it's not your field necessarily, but what do you think? We don't have the will, but let's suppose that we have the will. We decided to go for it.
Generally, when we have the will, things happen, right? Think about the Manhattan Project, right? They had nothing, and then in like 3 years, they had the bomb, okay? So if you really put the resources and you want to do something, you have it. The problem is that today, if we look above the ocean, we have a crazy president doing crazy things. So I don't see how we'll have a push, for example, for clean energy or any sort of progress when he's going back to coal, gas, and petrol, right? So
Okay.
crazy times.
So we shouldn't wait for, how to say, to be worse.
We should
than-
not wait for America anymore. I think we should wake up. We Europe should wake up.
Okay. I will go back a little bit to the topic, tonight's topic that you chose, from Galileo Galilei to the thermonuclear fusion. And again, I will ask you again, even if I asked you during the interview, what's in between these two extremes?
Yeah, so in this respect, as you understood, she interviewed me for the radio,
Yes.
for the cultural
yeah.
Romanian radio. So, and some of these questions she already asked to me, so you can compare when you will listen, if I just say different things. So, it's not, but I try to remember what they do.
No.
Ask twice the same thing. No. So, which was a question? Say it again. And now
What's in between these?
Oh yeah, between the two. Yeah, this title from Galileo to nuclear fusion, it's clearly a little bit ambitious and dangerous too, because it's we started at 7 o'clock, and indeed, if we had to talk from Galileo to nuclear fusion, probably we have to spend the night here.
You didn't tell me it's dangerous. during the
Yeah,
interview,
no, I didn't
so-
tell, but
Okay.
because but for the people who are here now,
Okay.
because I knew that your broadcasting was 20 minutes, so it was over anyway. But in this case, if Tom allows, we can stay here 24 hours, but probably we will be alone. So anyway, joking aside, from Galileo Galilei to nuclear fusion, there is, I would say the entire modern physics, which starts indeed with Galileo Galilei, who is the father of experimental method, and we go back to the experiment that we discussed before. And nuclear fusion is basically the future. I picked nuclear fusion as an example. Of course, you could pick other things, dark matter or other topics that represent the future of physics. So in between, there are around about 400 years of physics and science studies that have allowed us to talk, to interact a lot with nature, to discover a number of things, and I would say also to live better.
Stefan, what do you think? What is your view?
Well, you just put all of physics in front of us. I mean, the view is very, very broad. I mean, yeah, it's stunning that it stagnated for a while, big while, and then out of the sudden it was an outburst. And so, yeah, basically we started from Galilei, and then we had like big names like Newton, and basically we entered into the modern age.
Shall we think about Galileo Galilei as being also both two in one, theoretician and experimentalist?
Oh, for a long while, people were like both. And theoreticians were fashionable starting basically since Maxwell, if you think well. Before that, I mean, and what must be said, until Einstein, people were really looking down on theoreticians.
Indeed, about Galileo, theoretician and experimentalist, I have a quick story to tell that concerns Galileo and failures, in this case because of wrong beliefs. And there is a person, his name is Giambattista Riccioli. He's an Italian. He was a priest, a Jesuit priest, but he was also a physicist. He was a bit younger than Galileo, but not that much. He lived in the same period. And despite the fact that he was a priest, a Catholic priest, he was very much into physics, and he was a scholar of Galileo. He read all these books, and he was the first to perform in a reproducible way the experiment that Galileo theorized. For example, all the experiment about the free fall of bodies. There is this, I would call it legend, that Galileo did it from the Tower of Pisa, but this probably was not true. But the first one, which is the first person and that is documented that did it, is this gentleman. And the story was pretty interesting because he had to, measure how much time it took for a rock or whatever to fall from the towers. Bologna at that time had a lot of towers, still has some of them, but so he went up. But the problem is that he didn't have any stopwatch. The watches were invented after the pendulum, So there were no, so to measure time and to measure short times was not very easy. And he found a very clever way. Of course, he used the pendulum, but the point was that he had to calibrate the pendulum. So to every, Galileo says that all the oscillation of a pendulum have the same duration, and that's the principle on which all the watches these days work. But at that time, he had to make the calibration. And so the only, fixed phenomenon that he had to calibrate was the day. He knew that from the one sunset to the other sunset, it would have to taken 24 hours. So basically, he had the pendulum going for 24 hours. He counted the number of oscillation and then divided 24 hours by the number of oscillation and obtained how many seconds was for every oscillation. But now, try to imagine what it means to observe a pendulum for 24 hours. He asked the help of his fellow priest, and at the beginning everyone was enthusiastic, but then after the third time, because he wanted to be very sure, and the third time when he said, now we have to stay 2 days in doing that, it seems like that only one of the priests remained with him. Other probably say something that is not very appropriate for a priest, and they left. Anyway, he was a very thorough experimentalist, so he really confirmed all the Galileo's prediction. But why I'm talking about that? Because he was a very clever physicist, and he also made a theory about the fact that if you that the motion of he was thinking to a cannonball was deflected by the rotation of the Earth. And this is something that now we physicists know very well. It's called the Coriolis effect, and it's named after a French engineer that discovered that effect in sometime in the 1800s and in the 1700, in the 18th century. But Riccioli had noticed that, had made a theory about that, and it's very interesting that at that point his ability as a physicist conflicted with the fact that he was a priest. So, and at that time, Church had a geocentric view, cosmology, a geocentric view of the universe. So the Earth was fixed and everything else was rotating around the Earth. So he basically concluded in saying that, well, my theory would demonstrate that the Earth is rotating, because according to my theory, a cannonball which is sent from from the equator to north would deflect. But since the Holy Bible says that the Earth is not rotating, clearly my theory is wrong. Of course, to his justification, he had no possibility at that time to make precise experiment. This effect with cannonball is basically not visible on the short distance. But it's interesting to say that his failure in this case was that he believed more to his faith than to his brain, to his mind.
Then to the evidence.
Yeah, and of course he didn't have really evidence at that time, but he got it right. And these days, if he was more brave, we would have instead of the Coriolis effect, the Riccioli effect. Of course, at that time, also to his justification, we should say that being against the church on this matter was a kind of hot topic, but literally hot because they burned people, that did something like that. So, it's understandable that he was a bit scared about this point here.
Well, this is not quite a mistake. We cannot call it a mistake. Maybe it was a kind of adjustment to the times he was living. Professor Piero Martin is the author of a very interesting book. Sounds very interesting. It wasn't translated yet in Romanian, but you can get it in Italian. Storia di errori memorabili, the stories of memorable errors. Of course, in physics. Yes, you are speaking about physics, chemistry, in sciences. Let's talk about errors. Let's talk about errors, and I would like you both to point some. We will not have time enough to speak about everything, but let's point some really memorable errors that, how to say, in a way changed the course of sciences. They didn't destroy us. And because I would like in the end to talk about how much we need to allow us to make errors, especially today in science, when everything depends on money, on technology, and so on. So are we, how to say, you, scientists, physicists, much more constrained because of this? Do you pay much more attention? Are you careful, much more than before, and so you are not so much creative? A lot of things to discuss. Stefan.
So when you make a calculation error, that's just embarrassing, right? I think you asked about conceptual errors, like you want to step outside the comfort zone, you want to explain something that's not explained. For example, dark matter. A lot of theories, some are already disproved, nobody knows what it is, right? So this is a very good example where you have to make errors if you want to find something. You want to come up with a new model, you say, I think this fits, probably some will prove you wrong, fine. You made an error, you tried. Or if you do it right, okay, you'll be a celebrity.
So are you saying that, how to say, basically we are not afraid of making mistakes?
I mean, there are embarrassing mistakes, you know. For example, when
Of
you
course.
make something which is clearly stupid, right? But if you make something which, well, it could be, you know. I mean, basically since the 20th century, you are allowed to say crazy things, right? Einstein said that time is like a chewing gum, right? You can pull it, right? A space, it can be deformed. I mean, people thought he's crazy. And then finally, he's not crazy. They were crazy, right? Quantum mechanics, don't get me started. I mean, it's so crazy that, and that's what we have today, okay? So people kind of accepted that physics is crazy, and so you are allowed to be crazy, you know? And since Pauli, you know, Pauli postulated this neutrino, this particle which he famously said cannot be detected. Well, it was detected 20 years later, but he basically, when we knew just 3 particles, right? He said, hey, there's a fourth one, this one. And it was for good reasons, for the conservation of energy in the beta disintegration, right? And this kind of also opened the door to postulate new particles, because people say, hey, let's be crazy, let's put more. Right?
But all of this started from calculations, yes? From theory, mainly.
It started from experiment, actually, because in the beta decay, I mean,
yeah.
we know that energy is concerned, and now we know, and to the best of my knowledge, no one disproved it. And so in experiments with beta decay, they noticed that the electron that was ejected it has a continuous spectrum of energy, right? So where's the missing energy going? We did not yet know about the neutrino, right? So one solution had to be found, right? Bohr famously did a stupid theory called the BK's theory, where he said, well, actually energy is not conserved, it's in the average conserved. It took some years to be disproved. And then Pauli came with this theory, said, actually there's another body which you don't see, it is a neutrino, which barely interacts, or it doesn't, and steals away the energy. And it took like 20 years until in the 50s, 54 I think, 2 Americans proved it with the help of a nuclear reactor, where they had a huge flux of neutrinos, and this is how they proved that the particle actually exists. Okay, so Pauli took a risk, but I think a measurable risk, because he kind of said, this must be the solution. I mean, energy must be conserved. And then it's also about a sort of a inner religion, right? Einstein was believing in energy conservation, and many other physicists. He said, I will not give up on this principle. Why? Because he thought it's correct.
Because he thought it's correct,
Yeah.
but
Like, for example, Dirac famously, when he postulated the Dirac equation, he postulated this is the first order equation in space and time. Why? No one knows. He decided it's like this.
okay,
He
that
was
was
right.
the next question.
Because, yeah.
Do you, the physicists, decide that
When you want to advance, you basically say it must be this way, because there are so many ways it could be. At one point you say, I feel it, it's like this. And, well, you see what it gives.
So, from an experimentalist point of view?
Yeah, it's it's interesting the point that Stefan is making about the neutrino, because the neutrino has been also the subject of another very important experimental error in that case that for many people was considered as, for some people as a stupid error, but indeed was not. A few years ago, I think it was about maybe 10, 15 years ago.
With the neutrino
Yeah.
was the superluminic neutrino.
Yeah.
That was embarrassing.
Yeah, they were, there was this experiment where they produced neutrinos at CERN and in Switzerland, and they measure it in more middle of Italy. There is a big underground laboratory, and this was crossing the, neutrinos really are not stopped, and so they can easily cross from the Geneva up to Italy. Indeed, during some of these experiments, they had results that were suggesting that these particles were going to at a speed larger than the speed of light. Well, now one of the few things that up to now is really very solid in physics is that no things can go faster than light. So it's really a very hard speed limit. It's not a matter of tickets or measurements. It's just the fact that anything can go faster than light. So when they discovered that these particles were moving at a speed slightly larger than the speed of light, this was gigantic news, of course. And well, to make a long story short, I will give you the final result, but then we will do some other consideration. Eventually, the reason was a misplaced cable. There was just a very simple experimental error, and so the measurement was simply wrong, and so the result was not correct. So you may consider this as a stupid error or something that could have been avoided, but on the other hand, if you look to the entire process, it tells us a lot of things. And for example, the most important things that were recognized by the same people who recognized that they did the experiment and recognized that failure is that physics was able to show one of its best attitudes, which is to be able to self-correct itself. In fact, when they discovered the first result, they had two possibilities: either to continue not to communicate it and to continue the measurement and to check everything up to the very tiny level, and they would have probably discovered the mistake, or as they did, they publish it, and in the publication they were very honest. They said that result could imply a very new result, but they didn't say that these things were traveling faster than light. That measurement could imply this. So this immediately triggered a gigantic reaction in all the world, and a lot of people started to they applied the scientific method. They started to check the theory, they started to redo the experiments, because of course if they were true, it meant that Einstein was wrong, or at least in some way the relativity theory was at some exception. So the fact that they published this allowed the community to work on that. And in fact, after I think it was a few months, when a gigantic number of theories and experiments showed that it was almost impossible, they found a mistake. So you may wonder whether they did good or not. There is not really a definite answer whether they should have waited or they put it out in the community asking for how to say, correction or for verification of the result.
Yes, but if you check only in theory or by theory, can you prove that this is wrong? I mean, it's only the experiment that gives you the final answer, yes? If 3 experiments or 5 or 6 get the same result, then it's a proof that this is okay, yes?
If this was repeated elsewhere and you would find that the neutrino is going faster than light,
in theory or in experiment?
in experiment,
No,
then
okay.
But then it's, I mean, why you had this huge problem? Because this was gigantic. If you really were able to prove a particle going beyond the speed of light. So information basically traveling beyond the speed of light. It's over with Einstein, I mean, really over. You have to go back to the drawing board, you need a new theory, and everything collapses, right? So, but, okay, when I first read it, I was like, you guys are telling me that you are going at the speed of light plus epsilon, and you claim, I mean, if you break it, man, break it big, make it twice.
Not with epsilon,
Yeah,
I mean,
not with
yeah,
epsilon, I
of
mean,
course.
do something really gigantic,
Sure.
impress us, right?
Okay.
If you see, and I remember also reading other papers, I mean, somebody made some microwave experiments like 20 years ago or something, and the same thing, he found that it going faster than the speed of light. Well, you have to be careful, because depends on how crazy your wave is. You might have a wavefront, which if you cut the tail, right, and you have only the head, you say, oh, it went faster than the speed of light, but actually the center, where actually you had the center of your wave, you lost it. And that's what was happening. It was a sort of a tunneling effect. So you have to be really careful. So honestly, if you were to show me a new experiment where you violate the principle of maximum speed of light by a tiny, tiny, tiny fraction, you don't convince me. I mean, if it goes much beyond it, then okay, we have a problem. But
Okay.
this is probably some tiny adjustment where you didn't do it well.
But my point is, can you prove that something is wrong only by theory or only using
No,
calculations?
you need experiments. If, for example, you have a theory, you have one experiment, or let's say you replicate it twice, you show that the theory is wrong, it's over.
Okay. What other memorable errors are in your book? You also mentioned Einstein in your book, yes, Pauling.
Yeah, for example, in the very similar things happen with Linus Pauling, who is he's a very famous chemist, and he won 2 Nobel Prizes, one for chemistry and one for peace. He was very active in the campaign against the nuclear test in the 60s, and so that's the reason why he got the Nobel Prize. But he maybe could have got a 3rd Nobel Prize because in 1953 he was analyzing some microscopic pictures of the DNA structure, and he proposed a theory that described the DNA, which we know very well now is made by 2 helix. It's something that we teach at the high school, maybe even in the middle school. But he proposed a theory that said that DNA was made by 3 helix. And
Based on what? Sorry, based on what?
based on some images, microscopic images, that there is a very interesting story also about behind these images, because it would be long. As usual, nothing is simple. All stories are a bit complex. But anyway, he could have waited more time. He could have spent more time on that, and maybe he would have realized that his interpretation of this picture was not correct. But he decided to publish it, and more or less as did the colleagues of this neutrino story. He decided to make it public. And just 4 months later, other 2 scientists reanalyzed the same data and proposed a model in which the DNA is done by 2 helixes,
The double helix.
and the double helix. And so these 2 persons were Watson and Crick, and of course they were right, and Pauling was wrong. So they got the Nobel Prize, and Pauling was very open about his failure. He said, and there is I don't have the precise quotation, but basically talking with a colleague of him, he said, listen, if you have a good idea, it's always good to publish it, and because outside there is a lot of people that is there, a lot of smart people that will verify that, and so if you are wrong, they will find the error, as it happened, for example, for the neutrinos. But if it happened to be a good idea and you don't publish it, you miss the opportunity maybe to win a Nobel Prize. So he decided to take the risk. He was wrong, but this happens.
But he was already Pauling, so the community knows his values, yes, at that time. So maybe he, how to say, afforded to be wrong. Do you afford to make mistakes, such kind of mistakes when you are in the beginning?
If you ask me this, it means that you're implying that I'm not as famous as Pauling, which is of course very right.
It's up to you.
Yeah,
If you want, if you
of course I
assume
don't.
that you are.
Of course I'm not. No, you made a very good point, because in the book and also when you learn about these things, you always talk about these important people that made mistakes. And of course, a typical reaction is that, all right, if you're Pauling or if you're Einstein or if you're Fermi,
If you are already
well
Einstein,
established,
yes.
it's easier to fail, and it's easier also to take the consequences of failing. Of course, it might not be nice, because if you're very famous, you're very exposed, and so there is also some drawbacks. But anyway, let's put like that. If you're famous, it's easier to accept that you may fail. Much more difficult, and this morning I was with the students, is when you fail at a test and your professor give you a bad mark. So it's hard to convince him that, and to convince yourself that the same thing happened to Einstein also, because if you have to redo the test, and it has consequences. So I think we have to find a balance, clearly, but we should anyway try to teach, and it's something on which I personally insist, and both in the classrooms or at the university, and every time I have the opportunity to talk with teachers and with students, that we need to be tolerant with errors. Of course, not to accept everything, but to every time that a younger person makes something wrong, we should consider that when we were young, probably we all made mistakes, we would have done the same things. And so it's very important to accept that this happened and try to build on that in order to get new knowledge, which is basically what physics does. Even if you're famous or not famous, but...
Stefan, how many
Yeah,
mistakes did
contrary to politicians who never accept that they're wrong, in science you accept that you're wrong. And this is why sometimes you have rebuttals. I'm not talking about people faking data, for example, which were the famous guys who publish in Nature.
This was another topic.
Okay,
yeah.
this is not science. You are outside of the science, okay? If you are manipulating your data by hand, that's not anymore science. It's over. But let's say you make a mistake and people give you a reply and say, look, this is a mistake. Either they redo the experiment or they redo your theory and say, look, you made a mistake. You can just accept the mistake, and that's it. It can happen. Einstein made mistake in his paper. There are factors of 2 in some papers missing, which he quietly corrected later, and so on. So it happens, right?
So if Einstein failed once or twice, then it's okay to...
If you read even famous papers, you find small slips, which are not unimportant. This is why you have this erratum. You can publish an erratum of your paper. The journals usually allow you to say, line 17, equation this, there's a factor missing, and so on, meaning that it was a small slip. It's not like the whole paper is wrong. It's like you made a slip. Fine, it can happen. But you admit it, and we move on.
Did you make mistakes?
Yes.
When? In the beginning or now?
No, you make constantly mistakes. So honestly, if I think back, I should write 2 or 3 erratums to my papers. But there's some like small slips. But if you know the field, you kind of see, oh, he forgot the square root or something. But yeah, it happens.
And you physicists, do you start your career, how to say, taking into account the fact that you might make a lot of mistakes? Because I'm trying to understand if you need a special kind of education, because we don't live in a culture of not failures but failing. We are not encouraged to fail and to auto-correct ourselves, no?
If you want to stay on the safe part, you just make small steps and you don't take any risk. You make no mistake. You follow your PhD advisor, for example, who said, look, we're doing this. You continue doing exactly this, just small stuff, and you take, no risks. If you want to make a bigger step, you have to say, wait, I want to propose something. You might be wrong. So what? So if you want to, I mean, the big mistakes in physics were done by people trying to advance. The mistakes we remember today, nobody remembers tiny mistakes for things that were irrelevant, but we all know, for example, the cosmological constant of Einstein, right, which he called his biggest blunder, right? Maybe this is also an interesting topic, right? Why did he add it? Because he wanted to create a static universe, because he thought the universe is static and his equation would not allow this solution. So had this capital lambda, the famous cosmological constant, and then later when he saw the results of Hubble, that the universe is expanding, he said, this is my biggest blunder. And in the early 2000s, when he had these famous measurements about the accelerating universe, well, guess what? The constant is back, right? So it's a complicated story. So did Einstein make a mistake? Probably not. Who knows?
Who knows, yes. What other big names with big mistakes shall we mention? Both of you. I'm asking both of you.
So we should exclude the two of us, right? Because you want big names. Joking. No, well. Please.
No, I mean, I talk too much.
No, that's fine. For example, one interesting case that I made this morning, and well, I explained before the case of Riccioli, the case of Pauling, but you know, there are a number of failures or errors can happen for a number of reasons. Of course, we are not talking about criminal action, like you know, falsifying data, but in bona fide, this could happen for a number of reasons. So in the book, I try to explain various cases. For example, one interesting that I mentioned this morning, and I think is very valuable also for the message that it gives, is the failure that Enrico Fermi did in the work that Enrico Fermi, it's for those of you that don't know him, is Nobel Prize in 1938. He's a famous physicist. He's one of the fathers of nuclear physics. And in 1934, he got a number of results. He published them, and he got the Nobel Prize for them in 1938. When among these results, one of these results was about the discovery of elements heavier than uranium. At that time, uranium was considered the heaviest element. And he thought he had discovered an element, two elements, more heavier than uranium. And he talked about that in his Nobel lecture. But the Nobel lecture happened on December 12, 1938. Then since the day after he left Stockholm, he went to United States. His wife was Jewish, so she had to leave Italy because of the faces racial law. And by the time he crossed the ocean, he came to New York at the beginning of the new year in 1939. He learned about a paper that was to be submitted by another physicist. Her name is Lise Meitner. Mm-hmm. She was Austrian, but she was working in Sweden also because she was also Jewish, so she was not allowed to stay in Berlin anymore. And she basically understood that what Fermi was doing, was observing, were not elements heavier than uranium, but was the fission, the breaking of the uranium. So Fermi had observed for the first time fission, but he did not realize it.
Without knowing.
Without knowing, for a number of very good reasons. But interesting enough, when Fermi discovered this, which was, one of the results of the Nobel Prize, it did not make the whole Nobel Prize wrong. Just one part was not correct, a small part. But nonetheless, he decided to amend his Nobel lecture. And what I think is very interesting, and it's a very good lesson for all of us, is that if you go to the Nobel lecture, which is published still now online, you will find a footnote where he's talking about these transuranic elements and where he recognized, sorry, it was wrong. And, the ability of recognizing that you're wrong in particular, if you are a very, very famous person, it's not very easy, you know, and so it's not very common. So that's why I usually quote this example, because, you know, if Fermi was able to recognize that he was wrong, I think we can also be.
But maybe he knew that they cannot retract the Nobel Prize. They cannot get back the Nobel Prize from him. So maybe he was sure that he will still remain with the Nobel Prize.
Well, of course, you know, then we go back to the point that he was making. Clearly, if you think that the theory is completely wrong and you don't declare it, that's a criminal action. In this case, it was really, you know, a small part of the thing. It could have been just there. You know, the fact that he published in his Nobel lecture made this really public. He could, you know, if he had not done it, of course, he would have stayed within physics, within the physics community, would have been known by the physics, by the people who study history of physics. But in that case, he decided really to acknowledge for the public opinion. That's, for me, it's a very important point.
You want to make a comment?
Yeah, I mean, Einstein also was very open to admit mistakes. He had no problem with it. And speaking about mistakes, you started with the LIGO. So LIGO detected the first event in September 2015. They were afraid to call it an event. I mean, you have some interview with Ray Weiss and Kip Thorne, and they were like,
Yes.
they were reanalyzing and reanalyzing and calling people and say, did you inject a signal? No, because from time to time they were injecting a signal just to see if the system works. No, we did not. They checked all logs. It was too beautiful to be true, but it was a single event, so they were afraid. So then what happened? A second event came, and then they got the courage to announce the first one, right? So
They were lucky.
yeah, I mean, of course, they knew if it's true, it will come. These things happen. But, I mean, these top physicists, right, on top of a huge structure of excellent people, they were afraid to announce it because they said, what if we're wrong? What if this is not true, right?
So that means that we are not born with this, how to say, flexibility of recognizing, okay, I was wrong.
I mean, I must also say that they made the public wait for quite a number of while. This project was a very, very long project, and in 2009, I think they really had to convince Congress to finance them more to upgrade the LIGO, because they did it and they know they were like at the limit, maybe a very strong event, they'll see it, but it's unlikely. And they knew it's a very high risk. If they announce and then they have to retract, probably the Congress will stop financing them. So this is why I think they were extremely careful.
But maybe they were also so careful because LIGO is a very expensive and complicated event, and it's in 3 parts.
And America started to tune down their public money for research, so they know that they run a big risk if they have to retract a big result, a big announcement.
But going back a little bit to Fermi, what was Lise Meitner doing? Let's explain a little bit. How did she got to the conclusion?
Well, she was, I think, with Otto Hahn, no? Yeah. With Otto Hahn, they analyzed the data. And I think, I mean, Fermi. I mean, he was a good physicist, but I don't think he was a very good chemist. Had he done a more careful analysis of the products he had on those experiments, he would have found barium. And even a better one, krypton, which is going away. But anyhow, if he would have found these elements, it would shock him. And so basically there was another experiment, I think in Germany, where they found barium. And barium is like half the mass of uranium. And then what the hell is this doing? People are expecting in these sort of nuclear reactions that the mass is going either up or down by units, not by like it's cut in half. And then I think Lise Meitner got this idea that you could basically hit with the neutron the nucleus, which starts to wobble, and then it starts to break down into pieces. And she was even able to calculate the energy that is released per fission. Like, I think the estimate was 200 MeV, which is the correct one, very, very close to what we have. So at least at order of magnitude, she could estimate it, and which is huge. I mean, if you think that an oxidation energy is 1 eV, this is why the nuclear energy is so powerful, right? It's 8 orders of magnitude. And so this is how the things happened. And then, of course, you have the history of people who realized that wait a minute, we have a problem here, because if you can do this process in a runaway fashion, you can have a bomb.
Yeah, and of course the other important point is that in reconstructing these events, we should never forget about timing, because we tend, and this is true for in general when we go back to history, that we tend to analyze things with the with the eyes of today, and this normally we miss a lot of the complexity, and we picture everything on the same time. But the real thing that tells why Fermi was a genius is that the result that he obtained was in 1934. It took 4 years in order to reproduce the same things and to understand that there was a problem, and that there was a different process, and not and that what was he was observing, it was fission and not an element heavier than uranium. But it took 4 years, and in 4 years you can do a lot of things. You can advance, and it took 4 years in a time where this subject was at its infancy, was just starting. So a lot went on this. Yeah.
And I want just to add about Fermi. Fermi was the last great theorist and experimentalist. He was both.
Why do you say that?
But he also did the electroweak theory, right? Well, sorry, the weak theory. The
Yes.
weak, okay, it's not the complete theory, but given what he had for then, he published it in 1934. Famously, he sent it to Nature, who sent back the paper saying this is too much speculation. And he then published in Nuovo Cimento. Okay, and this is the first version of the weak theory, where the neutrino appears and so on. But he was also a very good experimentalist, and this is very rare. Today, you don't see it anymore. I mean, speaking about our laser experiments, they're so complex. I mean, you really have to learn only that. You don't have time to scribble on the blackboard or something. You really you have to be dedicated to this. Complexity just went up too much. Same thing goes with theory. You have to work too much to know a subject compared to these days.
Yeah, it's something that happens in a lot of disciplines, in a lot of, I would say, sector of human knowledge. Fermi was defined. There is a very nice biography. Maybe it's also translated there is in this bookshop, which is called "The Last Man Who Knew Everything." I think it's more or less the same. This is title, and this was true, and it was true for two reasons. Why? Of course, because people like him are not so frequent in the history of science, but also because at that time it was still possible for a single person to capture and to control, to understand the whole realm of physics. In fact, he was a great teacher, and he made contribution on a number of different subjects. Simply what happened in the last century is that the knowledge has extended. Physics has extended. There are so many things now that is basically probably not anymore possible for a human person to master all these different subjects. And this happens in various areas of science, technology, and in general human knowledge. It's a normal evolution, and it's exactly what he said. It's and this brings the whole theme of complexity, that all this part of interacting among themselves, and we have to find new way to understand this. And so we are called to be much more interactive and much more collaborating, because clearly it's impossible that knowledge stays in a single person.
But this is a very interesting point here. So this complexity that allowed this diversification, yes? Are you safer being so diversified and in the same time being more specialized on a teeny maybe area?
I think nobody asked us. This is how the society goes.
No, but how do you feel? Do you feel safer? I mean, are you safer?
It's annoying. It's annoying that subjects which are very close to mine but not really mine, I have to learn a lot just to understand. So in a way, it's annoying. And I was asking myself, when will science stop? And at one point, I think it builds way too much. Our brains cannot just take this amount of information. because it's getting more and more complex. Every small field is getting higher and higher. And then
okay.
fields are like just a tiny bit apart, but still everyone is going very high, very specialized. And at one point, I mean, you're like it's a very difficult job to jump from one to another.
Okay, and again, because you have to stay on your path, do you feel much safer on, how to say, you are not exposed to make mistakes? So much exposed to make mistakes?
I think it's not that important. I mean, it's
For you.
It's as before. I mean, it's as before. It doesn't matter so much if your field is narrow or wide. I mean, it depends what's your community. You know, sometimes there are some very small specialties in physics where you have basically 20 experts in the whole Earth.
Okay, and
then you have
also
others where we have 400, others like 40,000. So it's your community, right? It depends how big is your community and how much they are reading your papers and checking each other. Because at one point you're relying on your community. It's unlikely that someone outside of your community read your paper unless you're getting it too general and people can read it.
So, just 1 second. So, if your community is so small, then your mistake cannot get such an echo. Also, from this point of view, you feel safer, yes?
Probably. I never thought this way, honestly.
Okay.
And yeah, honestly, I'm afraid of calculation mistakes, which I might do. But honestly, if I will propose a crazy thing tomorrow and it's proved wrong, I'm okay with that. But I'm embarrassed if I do a calculation mistake.
Yeah, well, I think that the more general point is that we are simply more dependable on other people, and because you know, as much as opportunity advanced, you know, time advanced, we have more opportunities, but on the other hand, we depend more on other people.
From other fields or from your field?
Well, in general, you know, I'm here tonight. Tomorrow I will be back in Italy, and 2 days ago I was at home in Italy. So this is made, you know, if it was just 100 years ago, this would have been impossible. Of course, I have the opportunity to be here with you and to do these things, but this depends on a number of other people. It depends on, you know,
mainly on
transportation, on the pilot.
On Toma to organize the
yeah, Toma, but on
festival.
pilot to fly the airplane, and to people that produce the fuel for the airplane. You know, 200 years ago, it would have been depending much more on myself if I had the possibility to walk or to ride a horse up to here. So it was simpler to some extent, but of course with less opportunities. Now I have a lot of opportunities. Tomorrow I can be, for example, in the United States if I wish, but I depend on a number of people. That's the way, as you said, we have not been asked to do that. That's the way that, you know, society is evolving.
Okay. Do we have questions? Not yet. Maybe a few more minutes to discuss, because I won't. Toma, you don't want to ask anything? You don't want to ask anything? Yes.
If
we
you
can.
offer me the possibility, are you familiar, any one of you, with a classic science fiction writer? It's an American, A.E. Van Vogt. He wrote in the 20s, in the 30s, I think. Back then, 100 years in the past, he complained about the too narrow specializations that the scientists, the engineers had. And he invented I read his book in Romanian, so I don't know exactly how he named it, but I think it was something like nexialists, some kind of specialists that had knowledge from a lot of different areas, so they could tackle problems that those who were very narrowly specialized couldn't. What do you think about his idea? Do you think it could be applicable today? Do you think something like, I don't know, I hate to say AI because as I said in the morning, they are artificial but not intelligent, but let's say some artificial, some databases that could be integrated into our brain via some kind of neural link connection could help produce such kind of Nexialists?
Well, you know, it's a, I don't think I'm the best person to comment about, you know, science fiction, about bionic, you know, human being. But I want to make a more, you know, grounded, you know, a more, let's say, a simpler comment, which is that the possibility of knowing, of having a global view, it's going to be a luxury today, and which is something on which we have to think. I don't think I have a solution, but it's something that is very important for us as a community and for democracy too. If you think in terms of wealth, and in terms of jobs, for example, the jobs which have a lower payments, lower wage, are normally the more specialized job. The more poor you are, and the more narrow is your view, is your job, you are paid to do a specific job. In order to have time, to get time to think in a broad way, you need to be rich. You know, you have to you need to afford these, and normally this is connected with wealth, which is not a good thing, because we basically leave the possibility of a broad view of mastering the complexity only to rich people. You know, people that can buy their time. You know, time is a more scarce resource these days. A lot of us are paid, they live just to make a very specific task. And if you go a little bit off that task, you know, people are not happy. And this is something that, you know, has always been like that in the capitalistic society, of course, but is getting worse and worse these days. So it's something that, for example, when we discuss, when we train our students, our young people, we have always to keep in mind to educate people to get as much as possible a broad view. But of course, having the luxury or the possibility of having a broad view needs time, which is expensive, and needs a possibility of failing, which is something that you know, society does not recognize. So I think that you got a very important point that goes much beyond science, but it has to do with our way of life and with our community life.
But actually, do people want to have a broader understanding of things? Actually, capitalism and productivity and so on, productivity gains, I mean, brought us a lot of free time. People now have a lot of free time. They are much more freer than, I don't know, 50 years or 100 years ago or 200 years ago. And what do we do with our free time? We are all digital creators. We are making videos for TikTok, and we are dancing in front of our cameras, and we are using our free time for this, not for gaining a broader understanding of things.
Stefan?
I mean, yeah, if you look at the statistics, you're totally right. We're using TikTok to make stupid things, and I don't know how many people followed online lectures from big American universities. They're online since, I don't know, 20 years ago. MIT put online all the courses, and honestly, I followed some of them, and they're extremely interesting. So these are fantastic times if you want to get information. But of course, you get also misinformation if you got also tell. But this comes with the age. But I want just to return to AI. You were speaking about AI. Let me give you an example where AI 15 years ago, was used in quantum optics. So the group of Zeilinger, who got the Nobel Prize, he had a postdoc, Mario Kren, and he was really into these ML stuff and proto-AI, and they were working on some experiments with 4 entangled photons. I didn't have time to speak about entanglement. Entanglement is this crazy correlation at a distance allowed by quantum mechanics. And so they were trying to see how much they can do, and they found out, like, I don't remember, like 4. And then Mario said, let me write the code and run it. And so they created a software, they called it Melvin, and it's online, you can use it if you want. And they let it run for, I don't know, quite some time. And Melvin tested 120,000 experimental setups possible with 4 nonlinear crystals, and came up with 4 more solutions, which they didn't see. I mean, Zeilinger, the Nobel Prize in Physics, didn't see them. And Melvin found them. And then they were like, oh, right, correct. So sometimes AI can just guide you. Sometimes AI can, in a very messy expression or in a very messy experiment, can just test everything you don't have time to test and give you the solution.
And not only time, and the,
This is computing power.
Yeah, but in a more smart way. They put a lot of conditions. I mean, it's more evolved than just a test. Okay, it can self-adapt and so on. So these are quite smart stuff. So, and yeah, seeing the speed AI took, I wouldn't say it's not thinking. We might have surprises in a number of years. I'm not so sure anymore. I was also thinking the same thing, but now I'm doubtful. Seeing the recent progress, we might have surprises.
so maybe in the end it's only up to us how do we see these things, yes? How do we use, and what,
Yeah, of course.
what words do we
Any tool
use?
is dual use. Any tool is dual use, right?
Yeah.
So you can decide what to make out of it, right? The internet, you can use it to learn things you don't have money to pay, for example, American universities, or you can watch just people jumping on their head on TikTok.
So then, from this point of view, you say that, or you expect that AI, how to say, to help you in the way that, in the sense that you will get more results, more quicker.
I mean, in the recent papers that I submitted, I had to swear that I didn't use AI, right?
Mm-hmm.
So you have now a criterion to say, was part of this paper AI generated? Was part of this experiment AI generated, and so on. So you really have to state now that it's not AI, and I'm afraid, I'm suspecting we already have AI generated papers, but we don't know.
Is it possible?
I'm suspecting. I'm not sure.
Okay. What do you think?
Which honestly, it's a cheating, right? If you use AI and you put your name, for me, this is totally cheating. If AI wrote you paper, AI made everything, I mean, that's just plain cheating.
Absolutely, but this is, how to say, a higher level than just, mocking and inventing.
Of course, AI sometimes hallucinates, so you can publish stupid
Yeah.
things. So.
Well, I see that the discussion is getting really very serious. So I want to make one point, because about the which is a real story actually about cheating, which was not cheating about authors in papers. I have 2 cats at home, 2 red cats. So I like cats, and this is some, cats and physics have a lot of connection.
Schrödinger.
Physicists killed a lot of Schrödinger's cats, of course. But there is, in 1970 something, I don't remember, there was an American physicist who wrote a paper, a very serious paper, on Physics Review Letter, and with his name. It was a very good job, very good work, and it was accepted for publication, but he made a mistake. So, because it was a single author, and we used the plural, so in the text. So he said, we did this, which is sometimes, just for modesty, people do it, but anyway. And the publisher told him, well, no, this is not our style. If you did it by yourself, it's only single author. You have to write to correct everything. Well, at those times, Word didn't exist, so you had to really type everything. It was a few pages, and he didn't want to do. He explained this story later. It's not a legend, it's true. He didn't want to retype everything, so instead he thought that it was much easier to add one author, and he'd add the number and the name of his cat. Of course, he mocked it up a little bit, but the first name of the second author was Felix, of course.
Felix the
And,
cat.
Felix the cat. And he resubmitted things, and this paper is still available with the name of the cats. Because so in this case, the we was totally true.
So it was not a lie, it was not
No,
a
no,
mistake.
it's true,
No,
and
no.
it's the only cat that has a Google Scholar page.
Yeah,
You can find the citations of this cat.
Yeah. So no, but
Not
there.
yet. Not
Well, I don't know, but probably to some extent yes, given what they do. But certainly, my two cats have names that have to do with physics, and in particular with my field, because I'm working on fusion, and in fusion we try to fuse deuterium and tritium in order to get an alpha particle and a neutron and energy, of course. Deuterium and tritium are two isotopes of hydrogen, so they are very similar to hydrogen. So when I got these two, they are two brothers, very little cats. I said, well, to some extent, they have to celebrate, my discipline. So you all know that it's very difficult to be listened by a cat. They're not the kind of animal that listen to you very simply. So, suppose that I called my cat Deuterium. By the time I call the cat, he's already somewhere else. Deuterium, come here. Deuterium, come there. Or even if I call him Neutron, Neutron, come here. And so eventually I decided to call it the alpha, and tritium. So my two cats that's much shorter. So I have also the alpha cat. That's
Okay, the alpha cat is the alpha cat.
it's the
Actually, or it's not.
To some extent, a little bit. He eats more than his brother, so to some extent, he's the alpha cats. But let's put it this way: they don't have too many opportunity to show that he's an alpha cat anyway.
Well, at least the discussion from this evening shows you that physicists are humans also. So they can act like humans. This is one of the points that a few years ago at one of the press conferences in Stockholm with the Nobel laureates, one of the journalists asked one of the laureates, "Professor, you are still a human being, so tell us something from your life." Okay, we will wrap up in a minute. If you don't, are you sure you don't want to ask questions? We have.
Thank you so much for this discussion. It was really interesting for me to see scientists that can speak in plain terms, so us that don't study science can also understand it. It was fun, and I truly appreciate that. I wanted to ask you, because you mentioned in the beginning the times where people were afraid to, to come forward and contradict what the church was saying. But nowadays, a lot of the research is based on grants and on funds you receive. How does that impact the ability of scientists to admit to their mistakes where they know the grant can be impacted by this? Thank you.
Yes, are you much more careful? The creativity is gone. How does this impact?
Well, I don't know. I think it's difficult to give a general answer. Certainly, the fact that a lot of research comes through grants to some extent can direct the areas of research, can favor some area with respect to others. So this is clear. That's why I think public research is extremely important, and so I'm a big supporter, of course, of public research. This, I admit also, this is not the way things are going, also in fusion. For example, I'm a bit concerned about the fact that there are more and more private companies entering the field, and so, of course, they put their own money, they put a lot of money, but, they ask for particular results, for particular fields.
But maybe they can speed.
Yeah, they can speed, of course, everything. As you said, it's another example of how, reality can be complex. It's clearly more money comes, but there is also it's more target to some extent. But certainly you rose a good point. That's freedom of research with private money and with grants system can be a little bit a risk.
Ștefan.
Yeah, so 2 points here. First, it's, let's say, selection of the projects. And then if your government has an ideology, it might push back on something. For example, Trump administration and climatologists is basically a war against everything which has to do with climate, which is a disaster. And then
vaccines.
the second point is, in any normal project, you have a chapter where say failure. How can you report that you were good faith? You did it, but it didn't get out. Because if not, it's not research, it's production. If you're doing research, you have to admit you will not be 100% efficient. Right? Sometimes you don't get the results you want. Of course, typically you tune it. If it's not great, you still say something and the grant is fine. But if you completely miss it, probably it was very ambitious, but you still have the chance to say, look, we did the best, but let's say the experiment didn't turn out how we wanted.
But being very ambitious is not wrong necessarily.
It's not wrong necessarily, but for example, if today you will apply for a grant for something really, really ambitious, it's unlikely you'll have it. Because
No, but it doesn't mean it's wrong.
No, but typically you fund things which seem feasible. And with limited money, usually you fund things that are feasible. Now, to be honest, today we don't know where to look in theoretical physics, right? Because we don't have any more experiments that contradict what we know. So everyone is making hypotheses. Dark matter is the better example. Probably we have, 1,000 possibilities of dark matter theories. Some were disproved, some could be, and so on. So if you don't have a clear experiment, from astrophysics, you have all sorts of measurements coming, and they fine-tune and then retune and fine-tune, and some theories fall back, and some theories are forgotten, and other theories are good, and so on. It's a continuing moving field. You don't know where to look, right? Dark energy, it's even crazier, right? We're based on those supernova explosions, and now they kind of retuned it a little bit, so it's not expanding so fast, but it's still expanding, accelerated. No one knows, right? So.
But we know that the universe is expanding
That is expanding.
faster than we thought.
Okay, since Hubble we know it's expanding, right, in the 30s, but we have absolutely no clue, and as a theoretician I have no clue what the hell is this thing that is like expanding like a sponge which you release. It's expanding in an accelerated manner, and this is crazy because gravity is attracting, right, it's not repelling. So what the hell is repelling? I have no idea.
Actually, it was a Nobel Prize a few years ago on that proof that the universe is expanding faster.
Yeah, this is the three American
yeah.
astrophysicists. I think they published in 2000 or something, and they got a Nobel Prize like 15 years ago or something.
So then, you are going back to one of the points I made in the beginning. You are depending on the experiment.
It's a loop. Theory and experiments go hand in hand. This is how physics goes. Physics is a science of nature. If you make a theory and you have a single experiment, correct one, which disproves it, we forget your theory. We need a new theory. In mathematics, you can do whatever you want to, as long as you have some logic and so on. You can invent more and more complex spaces, more and more dimensions, and so on. In physics, you are bound by an experiment, and experiments today kind of reach the limit, at least in high-energy physics, for example, and new particles and stuff.
At this point, you're the boss. I'm just checking the time because I'm afraid that their hunger is expanding at a speed faster than the universe. But
shall we stay a little bit more? Do you have questions? Are there any other questions? There is, yes. You pass the responsibility. You don't want to answer.
I just wanted to ask you what you think about cold nuclear fusion, because there was a time when they pretended that they discovered it.
Yeah, thank you. You made a very good point because in that case, well, first of all, I made a different consideration that it happened to me this morning. When we went to the school to talk to the students, and those students are, they were between 15 and 17 years old, so they were probably born after 2005, 2008, more or less. And I like to to talk with students, but it has a downside that every year they turn younger. I don't know why, and of course, we physicists like to observe things from two different point of view. Of course, they're always the same age, unfortunately, and getting older. And this morning, I was embarrassed because I wanted to make this example, and I realized that to talk about cold fusion to person that that are 15 years old now, so they're born in 2010, is to talk to them about something that happened more than 20 years before they were born. So it's really a long time. And in fact, probably a lot of them didn't even know about what cold fusion was. So it's one of these examples where sort of tells you, of course I'm not implying anything about your age, clearly, but you are a very much informed person. But about my age, yes, because I lived that period. I was already working at that time. I was a young scientist, but I was entering into the field and I was scared about that news. I clearly remember it was Easter time when it came out in the newspaper, and I think it was a Sunday that, I was reading the newspaper. I said, I lost my job. I just got it since 1 year and I immediately lost. But basically, the story was that in 1989, I think this happened or 88, I forgot, these two scientists claimed that they had reached fusion at room temperature within palladium. The point was that this was wrong, but the bad news is not that it was wrong, as we discussed the whole evening. It happens to be wrong, but the fact is that they insisted this was not wrong. And so since then, they themselves and other people after them really keep trying, and to some extent also not really saying the full truth about the experiment. So there were also of some part of misconduct in that experiment that was really very bad for science, for our field, for physics in general, because people, of course, believe to them. Because, if you're a scientist, if you say something of that importance, people tend to believe. But different from the people of the neutrinos we talked before, and different from Fermi, they never recognize. They keep saying, no, we are wrong, and we are right, sorry, and we are producing infinite energy. Unfortunately, it was not totally true, but still now, 40 years later, 45 years, almost 40 years later, people still remind this story as a bad thing about fusion. So so that this example, and thanks for having made this point, tells that we have always to be very careful, because it may happen that you make mistakes, but this is acceptable only if you recognize this and if you are in good faith. In their case, I think that good faith was not probably into the business.
But they were, that was their child and they believed in no?
Probably they made an obsession about what they did. I just want to say one thing about free energy. If you type free energy generator on the internet, you'll be just full of options. Many people claiming they can make free energy. Mm-hmm. And honestly, if just 1% were right, there would be no more energy crisis in the world, honestly.
Yeah. Okay. No more questions? No more questions. Are we ending? Okay.
You're the boss.
You're the boss.
Well, we are the boss, but I was thinking that maybe.
Thank you for tonight's talk. Vă mulțumesc pentru prezență. După cum v-am spus, este de-abia a doua zi a festivalului. Mâine vă invităm tot aici, tot de la ora 19, la o discuție cu un geofizician. Este vorba de Răzvan Caracaș, care ne va vorbi despre Amintiri din copilăria Pământului. Răzvan este specializat în simulări numerice de geologie, de mineralogie și încearcă să descopere cum arată sau cum arătau la un moment dat în trecut suprafețele, dar și interioarele diferitelor corpuri cerești, Pământ, Lună sau, de ce nu, planete extrasolare. Sâmbătă vom rămâne tot în domeniul astronomiei și vom discuta despre obiecte intergalactice care trec prin sistemul nostru solar. Poate ați auzit de Oumuamua, sper că îl numesc corect, de Borisov și de noua cometă Atlas. 3 obiecte care, deși existența lor a fost teoretizată de mult, de-abia acum au fost detectate și dovedite ca făcând parte din, sau venind de undeva de la distanțe de ani lumină, sute de ani sau mii de ani lumină departare de Pământ. Pur și simplu sunt obiecte a căror viteză nu le permite să fie pe o orbită închisă în jurul Pământului. Deci știm clar că vin din afara sistemului nostru solar. Întâlnirea va avea loc sâmbătă de la ora 17. Atenție, va fi mai devreme aici, de la ora 17, și va aduce aici 2 astronomi. Pentru duminică este o mică, trăim așa într-o stare de superpoziție cuantică, pentru că sunt niște probleme legate de confirmări. Urmăriți site-ul festivalului www.bucharest.sciencefestival și sperăm că vom stabiliza această stare, vom trece la un sistem macroscopic stabil și atunci vom ști ce se întâmplă duminică după masa, că și discuția e planificată tot pentru ora 17. Dacă vă pasionează mașinile de pompieri, sâmbătă între 10 și 14 puteți vizita stația de pompieri, detașamentul de pompieri de la Băneasa, este în București, deși se numește Băneasa. Iar duminică veți putea vizita baza de elicoptere a Ministerului de Interne de la aeroportul Băneasa. Detalii tot pe site. Vă mulțumesc și vă doresc o seară bună.
And maybe if you allow me a final word, just to thank, of course, Toma and the Bucharest Science Festival, the Italian Institute for Culture, that is represented here by the director and other person, vice director. It has been really a great opportunity for me, this cooperation among these 2 institutions. I really had the opportunity to see a number of, in a short time, a number of very important aspects of scientific outreach, radio, and then this meeting and this morning in the school. So it was a very rich program. And of course, so I really like to thank once again the Bucharest Science Festival and the Italian Institute for Culture, and of course also this library, this bookstore for the hospitality, and that's been really great. So thanks, I'm really very attached. I'd already told to some of you, one of my first PhD student was he still is, of course, a Romanian person. He studied in Craiova, and now he's working in the United Kingdom, and he did his PhD thesis in my group, and we are still very close. His name is Alexandru, and so there is this relationship that started many years ago, and now it's revitalized, so really thank to everyone.
You are welcome to come back, and next time when you will be in Bucharest, you should take time to go to visit at ILANP. Yes, in Magurele.
Thank you.
Thank you.